Okay, this is the first discussion on the basics of magnetism. We will explain how permanent magnets work. It's very short, simple. Most of the focus of this chapter will be on electromagnetism. Okay, so before we get to permanent magnets, let's review the fundamental forces that we've looked at and add to it magnetism. So we've already looked at gravity and electricity, and we can ask two basic questions. What causes the actual force, and what does it act on, and what direction does the force generally act? So for gravity, we know that if you want a gravitational field to exist, you need mass. Okay, so the fact that objects have mass means there's a gravitational field associated with it, and of course gravity acts on other masses. The direction of the force, well, that may sound ambiguous, is we're basically asking, does it attract, repel, or do both? And we've learned that gravity only attracts. Okay. Electricity is ultimately caused by the fundamental property of matter, charge. And we already know that charges can either attract or repel. So that leaves magnetism. What gives rise to magnetism, whether it be in permanent magnets, electromagnets, etc.? Well, it's not obvious what they have in common. What it ultimately boils down to is that magnetism is due to moving charges. And like electricity, magnetism can attract and repel. So moving charges we will see, and it makes more sense with electromagnetism, with current moving in a wire or with streams of charged particles. In a permanent magnet, it's much less obvious what's going on because there is no current flowing generally in a permanent magnet. So we want to be able to differentiate between that and a regular piece of iron or any other metal. So let's talk about case one, permanent magnets. Something we're all familiar with, but would have a very difficult time explaining how they work. So the key thing is you have regions of atoms called domains. Okay, and these domains act like regions, or act like tiny magnets pointing in a certain direction. This is very, very simplified, but it gets to the heart of what a permanent magnet does. So if we take a bunch of bar of iron, you have just these arbitrary regions. And in those regions, you have an overall magnetic field due to moving electrons that are orbiting the atoms of a particular metal, in this case iron. It's not just any electrons, it's really the valence electrons. So if you look at their total contribution of magnetism in any given domain, they are affecting each other, but different domains are acting in a random fashion. Okay, so the overall effect of all this is you get no net magnetic field. However, in a magnet, things are very different. The domains are all more or less aligned. So one could ask, then how would you cause these magnets to be aligned? At least they should look like they're aligned. Not very good here. It's because this magnet at some point has been exposed to a strong or weak magnetic field. The stronger the field, the better the alignment. So when it cools and solidifies, then generally that magnetism is frozen into it. And it will stay like that indefinitely. So that's really ultimately the difference between a magnet and a bar of iron. With the iron nail, you can make it temporarily magnetic by rubbing it with the magnet, or even holding a magnet to it, and what it will do is align some of the domains within an iron nail, and it can be used to pick up other small metallic objects like paper clips, thumbtacks, etc. So let's see a quick little video of that, just to make it a little bit more clear. That is some awesome slow-mo. So very, very basic. What kind of materials do magnets respond to? Well, the easy answer is metals, but we know that magnets will not pick up any metal, especially any coin that has zinc, copper, aluminum, etc. So there are certain metals that lend themselves to it. So very, very simply, the key metal that is magnetic is iron. There are certain alloys that are particular. A common one is alnico. So that's an alloy of aluminum, nickel, and cobalt. And then perhaps the strongest magnets of all are the rare earth magnets. Neodymium is a classic one. Gadolinium magnets, etc. So here is a alnico magnet. This would be a rare earth magnet, the disc ones that are neodymium. And then we have cow magnets, which are either ferromagnetic or alnico, which are used, we mentioned in class, fed to cows to attract iron. Okay, so any magnet you have has a certain property associated with it called polarity. And this is very different than charge. It's an analog to charge, but it is not the same thing. So any magnet must have a north and south pole akin to a positive and negative charge, but again, they are not the same things. Poles and charges do not talk to each other. Alright, and something you've learned a long time ago, like poles will repel and opposites attract. Okay, so here we have a bar magnet. There's a north pole, south pole. If I were to break that in half, I would still have to have two poles, where this pole would be a north and this pole would be a south, and so on and so forth. So if I kept breaking in half, this side would be a south, this part would be a north. Alright, so the last aspect of magnetism, or at least for permanent magnets we're going to look at, is how to map out a magnetic field surrounding a bar magnet or a horseshoe magnet or any other permanent magnet. The key to understanding the nature of that field is to know what the magnitude and direction is at any given point. So the easiest way to understand what the direction is with the compass. Okay, so whereas in electric fields we had a hypothetical positive test charge, with magnetism we can get something that's a little bit more concrete and real, and that's a compass. So the rule of a compass, and a compass is nothing more than a magnetized needle that's able to float and rotate about an axis, is that the needle always points toward the rule for a compass is that the magnetic needle always points away from the north magnetic pole. Okay, and again, it's away, not toward, and toward the south magnetic pole. So this seems to contradict what we often hear, that compasses point towards the north. That's actually a true statement, but we're talking about a different type of north. So if we're here, let's say somewhere on the Earth, and we point towards the north, what we're really talking about is the north geographic pole, where Santa lives. And that's where the Earth's imaginary axis passes through. However, nearby it, within maybe 100 miles or so, is a different type of pole, a magnetic pole, due to the Earth's core, or spinning core to be more exact, and that's a south magnetic pole. So if we hold our compass here at this latitude, we will see it points in its general direction. It's actually pointing towards the south magnetic pole, which happens to be the north geographic pole. So that's why we say compasses point north, when in fact they're pointing towards the south magnetic pole. And conversely, over here would be the north magnetic pole, and of course, where the penguins are, is the south geographic pole. So on this bar magnet here, if we label this a north and this a south, and you are asked to predict which way would a compass point, alright, you just follow the rule above, pretty straightforward. The compass needle would point away from the north and toward the south. If you were somewhere between, let's say right here, then you'd have to follow the rules of magnetic lines, which we'll do in a lab, but we've talked about before that the magnetic field lines loop around. So in a sense it would point away from the north and toward the south. But that's a discussion for another day. If you want to learn more about magnetism, I strongly suggest go to the Minute Physics channel on YouTube and watch the How Magnetics Work, or How Magnets Work. This goes into greater detail we talked about earlier. Also very interesting is the magnetic levitation and how to destroy a magnet. These are excellent follow-ups. They take about 15 minutes of your time and can enhance your learning.